In this video, I will record the second part of the solution of the data topography exercise. So it starts with the basic statistics. Here we want to print some basic stuff. So for example, what is the minimum of H? So let's print this. You can use the function minimum, and this will find the minimum in the table H. Of course, you can add some text, min of H equal H in unit meters. So that's a bit better formatted. The same applies for the maximum. So the maximum you reach with the function maximum. Make sure you apply it there too. That's the maximum height. And other basic statistics may include the function, the mean, and the median. So the next point is to define the spacing. So to define the spacing of the data, it's basically the size of one cell. We need to use the coordinate array. So we can use coordinate 2 minus coordinate 1, and this will give us the size of the first pixel. Note that the whole grid is regular, so all the pixels are the same size. So the size of the pixel in X can be simply x2 minus xc1, and in Y you use the Y array. You can print also this information. There we go. What is the size of the pixel in square meter? So we know the size of the pixel of the cell in X and in Y. The surface is dx times dy. And you get this number here. Then we want to compute how much of the surface is above 800 meters. So for this you can use indexing. So we want to compute first how many cells of the data set are above 800 meters. So we want to use H larger 800. So this will give us a table of all the H which are larger than 800 meters. Then we want to sum. So this basically tables of 0 and 1s, where all the 1s are above 800 meters. If we want to compute the total, we can make the sum of this. This will give us the sum of cells which are above 800 meters. If we want the surface, we need to multiply it by ds, which which is the size of one cell. So we have about 10,000 cells times the size of the cell. This gives us a total area of about 8.65 10 to the power 7 meters square. Surface above 800 meters will be this. There you go. Then we want to make a relative percentage with regard to the whole region. So how much of the total surface is above 800 meters. So we can take the surface, which is above 800 meters, and divide it by the total surface. So what's the total surface? The total surface is Lx minus Ly. So we can compute the length in x and the length in y, multiply Lx by Ly, and you get the total surface. So how to compute Lx and Ly? So Lx is xc, the last position in x, so end, minus xc1. This will give us the length in x. The same can be done for y. So now we have S800 divided by the total surface, and we can multiply this by 100, and we obtain about 7.2%. So we can, for example, write this message. .2% of surface is above 800 meters. And now we want to generate a histogram. So to make a histogram, there is a function in the plot package, and the function is simply called histogram, sorry. So let's make a histogram of H. In order to get the correct histogram, you first need to flatten the array H. This means turning H into a 1D array, and this is done by applying the colon symbol into the square brackets here. So the histogram would look like this, and of course we need to put some labels there. So we can add X label, will be here the altitude. And the Y label is the number of cells. Then the next part of the exercise, we want to compute the gradient of the topography. So to compute this quantity in Julia, you can use the function diff. So this array, we're going to call it hx. It's going to be h dx. So here we can use the diff function, and we want to take a derivative in the x direction. For us, it's dimension 1, so dims should be equal to 1, and this should be scaled by dx. We now have an array, and this array will be shorter by 1 in the x direction because we do a differentiation here, a numerical differentiation in this direction. So here the size is 402, it's not 403 as it was for h. The same operation can be done to compute the derivative with regard to the coordinate y. So we'll need to scale it by dy this time, and dimension should be 2. So let's run this. The output is this line is shown here. Here the size in the y dimension has decreased by 1 because the differentiation is done in the y direction, which is the second dimension here. So the two arrays have a different size, and we want to average these arrays. So let's do this, and we will average x, the hx to the vertex position. So let's do that. We take half of hx. This should be done in, this averaging is done in the y coordinate as explained in the previous video. So we take 2 to n and 1 to n minus 1, and we have half of it. For the y coordinate, we do the same, but we work with the y component of the gradient. So the averaging is now done along the x-axis. So the slicing is done on the first index of the 2D array, as you can see here. Now we have the array located at the same position, so we can compute the norm of the gradient of h. So for this, we take the square root. Don't forget to put a point here because we are working on whole arrays. So we are doing an element-wise operation. We are computing a slope for each of the nodes involved in these arrays. So we take the square root of this array with element-wise square, and this array with an element-wise square. Now we want to compute the slope in degrees, so we can take the arctangent. Again, it should be broadcasted, so don't forget the point here of S. Then the plot requires the definition of the inner coordinates, as explained on the video, and these are simply the mean of the XC array. So XC array needs to be sliced. Two to end and 1 to end minus 1. And the same applies to the YVI array. once we have this, we can make a heat map using the x coordinate, the y coordinate, and s. Transpose as usual. So now we have the slope, and here I've used the function atan, so the angle is in radians. Now let's make sure that the slope is in degree. So I put a comment here, so a tan, this gives radians, and to obtain a slope in degrees, you can use a tan d. This will give degrees. So we change this one, and there you go, you get a map of the slopes. Let's scale the array, the x coordinate in kilometers, the y coordinate in kilometers. We can also label, so x label, x in kilometers, and we can label y label y in kilometers. So now it's a bit more digestible, and we can add the title, slopes in degrees. There you go. Then also let's fix the aspect ratio. And the limits along the x-axis. X lim from 0 to 35 kilometers.